now we move to the derivation for the velocity of the harmonic oscillator. Okay, the same situation, except now we are considering the velocity of the object Q here. Okay, so for example, harmonic oscillator, if you are imagining that you are here and you are carrying a bicycle or car with a constant speed. Okay, so this is you circulating around a circular path. So at every moment, your velocity change. Even though your speed is constant, your direction always change, right? So since you have a constant speed, but your direction change, we say that you have a changing velocity. Okay, so that means at this point, your velocity direction is in this direction, and if you move, so for example here, your velocity is at this direction, and it keeps changing. So now we can just focus at this point. So your velocity is at this direction, and you have certain speed value, which is VQ. Okay. So the similar thing, because this is the oscillator is a shadow or the projection of Q on this axis. So this P now it's moving to the left because we are considering one dimension. So this oscillator going to the left, and this component of the velocity is equal to the component of the velocity VQ, because VQ we can resolve into two perpendicular components, which is one is here and another one is here, but we are only considering this component, which is this component is equal to the component of the velocity here. That means if we want to get the velocity of this P, we have to get the velocity of this Q, the projection of the velocity in this direction. Okay, so from this information, we can extract this as in the right triangle. So this is the direction, the velocity component that we want to have. Okay, here, and also this is the velocity of Q. Right, so theta here is equal because if you investigate, so this is theta and this is theta and this is theta. So the same value of theta here. Alright, so from here we make a right triangle similar to the previous one. But now we have sine because we have a opposite side divided by the hypotenuse. Then we have negative here because the x is to the left. Okay, so rearrange back. We have VQ sine theta, and theta is omega t because from here. So VQ is equal to V maximum. V maximum is the maximum value that the oscillator can have. So the maximum value of the, because we have from the previous lesson, we know that the oscillator change with, the velocity change with time. Here the velocity is 0, right? Because it stopped for a while. This is also 0. It stopped for a while here. But here it will be maximum. So when it here, that means it is like this. That means this is VQ, and this is the maximum value. Take this value. The same way if it's going to the right, it will also take the same value of VQ. That means Vmax equal to VQ. The maximum value of the velocity that P can have is negative Vmax. So we have a complete equation for this. Okay, from here again we make a sketch graph. So from this graph, okay, so let's investigate at the time 0 here. So at time 0 here, the P should be instantaneously at rest. That means velocity 0 here. So basically it should be 0 here. And then the velocity is increasing, but increasing in magnitude, but going to the left. So this side means that the P goes to the left. Okay. So to the left, but maximum still to the left. still to the left, but now it stopped for a while, and then going to the right, positive, and then still going to the right, but the decreasing speed to 0. So as this Q is moving here, its maximum, the P here, and continue for one cycle. And it will continue for another cycle because this is a periodic motion. Okay, so if you compare between these two graphs, so this side means that the P is on the right side. Left, that means P is in the left side. For here, this area means the object is going to the right, and this area means the object goes to the left. Go to the left. This is in which side? This is going where? Alright, so next,